welcome home again. And it's yours.
Thank you very much. Thank you, Nafi. Yeah, it's pretty happy to see all of you here. So yeah, but I will, after the pandemic, I mean, since the pandemic ends, so I will be back pretty frequently. Yeah, so today I will talk about the near thought. I think someone's talking. Yeah, but it's okay. Yeah. I'd like to talk about the near field ground motion modeling of the recent magnitude 7.8 Kahramanmaras earthquake and the impacts on local buildings. So I put a animation on the title slides, which is showing the ground field propagation on the surface of the Earth. So that's based on SpecFam globe. And to getting accurate ground motion modeling, we needed to just incorporate with the data and quantify the source mechanisms. So that's the main topic of the today. So today's topic will cover two parts. First, the near surface ground motion modeling for the earthquakes, that how we quantify the source parameters, and finally model the ground motion in the region. And in the next part, I will show you how to input this ground motion to the building and how the building will impact it from this ground motion input. And we will give you, just show you how to use the game engine to reconstruct the hazard scenario from the inception of the earthquake to the collapse of the building. So let's start from the near surface ground motion modeling. So this is just a rupture animation of the SCAC benchmark tool. And for the real near field just acceleration modeling, we should incorporate with this dynamic rupture modeling to finally get the accurate just the ground motions. First, some background information. So the Kahramanmaras earthquakes occurred in the Kahramanmaras province in Turkey, and the epicenter is in this part. And 3 weeks after this main shock, there are up to 10,000 aftershocks recorded after the main shock. And these earthquakes has catastrophic impacts on the local buildings, especially these provinces. For example, Kahramanmaras. So you can see the building collapse. It is the building picture before and after the earthquakes. And this is a Kahramanmaras. And this is Gaziantep and also Hatay. So later in our game engine-based hazard scenario construction, I will show you how to model the building collapse in Hatay region. So why I show you those 3 provinces? Because those 3 provinces are what exactly the East Anatolia fault goes through. And they really have just an extremely high acceleration, which is what the GMPE hasn't been predicted. So first, thanks for the AFAD to provide the open source data. So even we are in China, we can easily get this ground motion recording just from these very dense networks. So we have both broadband and strong motion data. But for the near fault region, so only the strong motion just the stations work, because all the broadband stations, they all just clipped. And so this is the acceleration data. So we just integrate that to get the velocity. Yeah, you will not see that clearly. So I will zoom in later. But just from the raw data, so in this showing the 3 component recording for the near field stations. And the y-axis is epicenter distance. So we can see that just by roughly look at the raw data, we can find 3 stages of these fracture ruptures. So the first stages from here, and the second stages, and the third one. So we can see that the third one has a really high accelerations. Even the station has epicenter distance over 100 kilometers. And this is because this fault process actually is very complicated. It's not just a single lab motion. It was initiated from this very small slab. People may not even notice there is a fault there, just until the very recent finite source inversion. So this is the initiation of this M7.8 earthquake. Then after the initiation of the earthquake in this small slab, two big segments was triggered, one in the northeast. So this is part of the East Anatolian fault. So this fault just ruptured to the northeast. And later, the third rupture was initiated. So that is this one. So this one is just a rupture to the southwest. And also this is what we are focused, since this rupture just goes through many big cities, including the Kahramanmaras and the Altep, and also the Hatay. And also look at the comparison between the ground motion prediction equation and the recording. So the red line here is what the GMPE predicted. So the ARCA and the Boole, so they are just the two famous or popular ground motion prediction equation. However, in this Turkey area, look at these dots. So these are the stations with accelerations just much higher than what the GMPE predicted. So we need to think why these stations have such high accelerations. So by the way, look at the epicenter distance. So they have the distance between 50 to 150 kilometers. So they are not stations very close to epicenter. However, they are the station kind of far away from the epicenter. So why this happens? So after we projected the waveforms into the geographical map, we found the reason. So look at this map. So these are the third segments of this Kahramanmaras earthquake. So this is a part of the East Anatolian fault. So this fault just ruptured the segment 3 of from the finite source inversion, and this rupture just the direction just going from the epicenter to the southwest. And I also plotted the waveforms as well the station is. So all these stations are along this Anatolian fault. And the red line is the north component, and the blue line is the east component. So as you can see that, so the high acceleration of all the stations exceeding the GMPEs, they are all the stations near to this East Anatolian fault. So that is the directivity effect, because that fault just rupture to a super long distance. It doesn't stop, it just continue to over 100 kilometers. That results in the high acceleration, even when the station is far away from the epicenter. So using the near field acceleration data, we are trying to quantify the source parameters of this segment 3. So why we don't quantify all the 3 segments is that because we don't fully finish the fully dynamic rupture modeling. So we have a collaborator. However, after we trying to incorporate the data with his modeling, it's kind of a delay. So in my side, as an observational seismologist, I use like a one slab model, which is easier for the inversion. However, our collaborators are still working on the 3 multi-fold patch dynamic rupture modeling. So we will finally compare that results with this. But even with this one slab Haskell finite source model, we can also fit the stations near the fault in a pretty great accuracy. but there are some exceptions. I will interpret that later. But for the most near field station, using this Haskell rectangular finite source model, we can fit most of the ground motion data. So we at least get first order approximation of the rupture process for this segment. Then let's zoom in to see the ground motion fitting. So as we can see, so that the red line is the north observation, and the blue line is the east observation, and the black line is our model. So I do some parallel comparison with our results with other groups, for example, the UCLA. So actually our one slab model, in the case of the waveform fitting, it's not bad compared to other results with the 6 slabs or even like a 3D. So yeah, but at least this first, the one advantage of this first order approximation is it's easy to construct the inversion. So also the results will be more stable. And with the quantification of this Haskell source model, we generate the regional ground motion map. So that is the ground motion due to the magnitude 7.8 earthquake. Again, so this is the kind of first approximation, just combining the waveform data. Yeah, go ahead. TK3123. Yeah, exactly. That's what I want to say. So I have a circle here. I'm glad you asked. Thank you. So exactly. So this is only a hard rock model. So, but for the Hatay, so in this region, there is a very thick soil basin. Also from the previous literature, so people actually have many like a soil core in this region to show in very thick soil layer. So we haven't incorporated that information, but we can easily incorporate that as just a transfer function into this model. So with the hard rock as kind of a source, and we can convolve with the transfer function representing the soil layer or side effects. So that's why in this very southwest corner, so the waveform have super long duration. Also, the amplitude was amplified by 2 to 5 times. Actually, that is what a paper from Turkey that's 3 years ago. So they started all the soil layers in this field. We haven't incorporated this information. But we'll do that in the maybe next month, just before we write up everything. But yeah, it's we also noticed that.
There's a very clear ring down signature in that waveform, those 2 bottom waveforms.
Yeah.
Is there a story about that? Is this a source signature effect, or is this a reflection echo somewhere in the propagation?
There, yeah, it's complicated. So there are 2 reasons. So first reason, also by discussion with our collaborators working on the dynamic rupture modeling. So in this region, there are many small slabs for the traces. So but they're still running that. For many dynamic rupture modeling, they found that in this corner, after they break the source to many small slabs, some small slab in a super small region, they reach the super shear, which means that the energy just will emit very quickly, which may result in this huge spike.
There's also the Mason geometry effect.
Yeah.
Very simple phenomenon.
Yeah. Exactly. So that will bring up a problem. Actually unsolved problems. How to solve the model? How to select the model? Because super shear can explain just this big spike in the super southwest position, and the side effects can also explain that. So my plan is just to construct those 2 models, also a combination of both super shear and the side effects, and let the data to generate the probability of different models. So that will come to the study of the model selection. But again, this is just the first order. So that's why I come here to discuss with all of the experts here, also some statistician, to finally we can construct a probability density distribution over different possible models. But this is the first order one. Yeah, so this is our ground motion modeling for the M7.8 Kahramanmaras earthquakes. Now let me advertise my project just funded about a game engine. So, but again, for the first part, just more like a detailed or just more simulation need to be run to get just a better interpretation or more conclusive explanation for this super high acceleration in very southwest part. But this project is a new one just funded to use the game engine to construct the hazard scenario. So we will use the Turkey earthquake as a showcase, just to show the workflow, how to use the game engine to integrate all the physics engine and make the simulation really real, and show people the hazard scenario from the inception of the earthquakes to final collapse of the building. So just the proposal call actually is due to previous people in different areas. They may work on different simulation separately. So for example, scientists working on dynamic rupture modeling, they only just focus on the things in the subsurface, just how the rupture goes and how the ground motion propagates. And observational seismologists, just most of them working on the data and from the subsurface to the buildings. And the civil engineering is working on just the input, the measured acceleration to particular structure and to model how the building can be shaken and how they collapse. So it's kind of all these physics engines, they are separate. So we may think about if we can bring all these physics engines to one. So then let's just come up to this idea of the game engine. So the idea, I wrote the proposal, but yeah, just found it. Anyway, the idea actually is from the video game. So this is a game called Cities Skylines. So it is a strategy game to let the users to build a city virtually. And there is a recent plugin called Natural Hazards. So that one, Natural Hazards. So this Natural Hazards plugin can have the earthquakes, tornado, fire, sinkhole, tsunami, and all these just the hazards we started in the university. So they put them in a game engine to make that visually just super nice. Although, I mean, as a seismologist, I can tell, so some mechanism of the earthquakes and some of the ground motions are super simplified. It's just a shaking table, just doing, provide the horizontal just a movement of the ground. But they really don't have the very nice basics. However, the visual is super nice. So for example, the thunderstorms, it's really just like a city. So that's the strength of the game engines. So it can build the cities and the natural hazard scenario just visually like true. However, they don't have the physics based. So that's why we propose a integration of the physics, the geographical information, the building information, also the ground motion physics-based ground motion modeling, also the structure engineering just engines together by this game engine. It's kind of we have the interface to get the output or the physics-based engine together and visualize them, showing people the entire process. Also calculate the seismic loss. So this engine actually can provide the governments or the researchers a way to just simulate like any hazards we want, and finally provide them just some suggestion. For example, after a big hazard, so how to like do the rescue for cities, and how to calculate the seismic loss, and how to just help people just got hit by this earthquake. So what we have now is we use this magnitude 7.8 earthquakes and the calculated original ground motion maps. So we input that to the game engine we have, and we're trying to reconstruct the hazard scenario. And for the building information, so I have a collaborator at the UCLA who is Professor E.T. at the civil engineering. So he has many like building inventories. So finally, we will collaborate to build the virtual Turkey cities in our game engine. But for this kind of preliminary tests, we get the building information just by guess. So we have pictures. So we kind of can just can guess what a structure and and we can count the stories of the buildings. So just like that, we build buildings in our virtual world by just looking at the pictures. And after we have the ground motions from our just geophysics engine and this building model from some civil engineering finite element or finite discrete element engine, we can combine everything together to make this hazard scenario. So I'll show you the video soon, but we tried 2 game engines. One is Unreal. So all these game engines, they are just open source. So everyone can use that to develop your own games and just programming that. So Unreal is based on the C++. So let's see what we did. Let's first move to the Kahramanmaras, which is here. And now we just fly along the fault. So you see the plane flying. Then this is the Hatay, so which we build some of the buildings, I mean virtually. Then we input the acceleration in the place. Since we have the ground motion modeling, so we can input the ground motion to any place that have the building.
So this gaming engine allows you to put in things like stiffnesses of members and shear walls. It was designed to essentially put in civil engineering information. It sounds very, I know these game engines can do impressive things, but it sounds very elaborate for what the game would be.
So theoretically, the answer is yes. However, for now, we only input the data, I mean the results from the civil engineering engine. And actually, we only write the interface. But theoretically, we can develop the engine and write the code to represent different like structure and stiffness of the just civil engineering just elements. But however, for that one, we just use the game engine like a visual tools. So for other physics engine, we pre-compute results and only store the results in your drive. Then the game engine is more like a visual tools. So we write an interface to just import data into the game engine. So this is Unreal. And we also have the other engine because now it's in the status we try. So the Unity and Unreal are 2 most popular game engines. So maybe 50% of the video game companies use Unity, and the rest, maybe 1/3, they use the Unreal engine. So this is what we made from the Unity. Let me play this. It's MIT. This is Boston. Then let's fly to Kahramanmaras again. So we're trying to the ability of the different game engine actually are different. Again, this is a Kahramanmaras.
Just out of curiosity, how large are these videos in terms of computer on your storage?
It's tens of megabytes. Yeah. But again, loading that, you really need a good GPU. But as far as it's packed, it's small. But when we develop that, sometimes it's stuck. Yeah, we have more buildings here. Yeah. So since these are the buildings with different stories, so the response may be different, and some of them fall earlier, some are just no. So actually, this will bring a question how to verify the simulation. So yeah, we have a couple of just answers for how to verify that. For example, we can use the seismic loss because that's what the government can have. So so these engines can live in your computer. So we can run the simulation again and again for millions of times. And to verify and select the model, so there are many metrics, and a seismic loss is one. So actually we can have that from the government report. So just because each building, when they fall, either they fall in a halfway, or they fall east or west, the loss are similar because we just lost the building, we need to rebuild that. So later we can use the metrics to verify, or it's a model selection to select the right. Again, for all the models are wrong, some are useful. That's definite. However, since these engines can live in our servers, so you can run that every day for millions of times. So finally, we can get a stochastic distribution of the seismic loss due to a particular earthquake. And this will be very useful for the government to just for the future planning of the cities. Yeah, go ahead.
The collapse there, that's computed externally, right? You're only.
Yeah, we calculate each building on different CPUs. Then we have the results of just because these are just timestamps. Then we import the timestamps into the game engine. Yes, since the game engine have good a rendering tool, so it can, but it's not perfect. We just initiate the project. Yeah, go ahead.
Did you only model one earthquake?
Yeah.
Because what happened?
There are
most recent case,
aftershocks. Yeah.
the first earthquake caused some damage, and the second one knocked down a lot of those buildings.
Yeah.
So in order to be more realistic,
Exactly.
You need to take into account both earthquakes. And did you also model the tunnel form of construction?
Which model? The
tunnel form. Because government
tunnel form.
built many tunnel form construction buildings, and for some reason they didn't get any damage whatsoever. So I would recommend that you should include tunnel form of construction in your modeling.
I see. Thank you.
Tunnel form of construction, basically most of the walls are like shear walls. So that is extremely important.
I see.
For earthquake resistant building in these regions.
I see. Yeah.
What is tunnel form construction?
Well, most of the
vertical walls
instead of columns, you have
tubes,
walls, shear walls all over.
shear wall.
Yeah.
Like the walls at the ends of this building are shear walls.
Yeah.
Whereas in this direction, where there's big holes through the windows, it's weak.
Yeah.
But in that direction, they have a slab going all the way down.
Yeah. Yeah.
So
in the tunnel form of construction, all the walls are basically shear walls.
Yeah, so that is just my new projects for the next 4 years. So yeah, I'm glad I have that, so I can build some games and play that myself. Yeah, so let's first I'll just acknowledge the funding source. So I got just 3 grants just recently, starting in January this year. So it will last for for my entire tenure track. Hopefully I will. I don't need to write any more proposals during my tenure track. That's great. Also, I thank AFAD and also Stardy to send me the data, so I'm able to run that. Just again, this work is incomplete. So I have other collaborations working on different things. So we'll make that just better and write up things probably in summer. Just a simple conclusion about the M7.8 earthquake. So first, there are many stations got a maximum PGAs just much exceeding the predictions from the ground motion models. And the waveform analysis just showing the directivity effects can explain the surprisingly high near field PGAs. And also we construct the hazard scenarios using the game engine and show people the entire process from the rupture to the building collapse. But there are some things we haven't just make that a very very complete. I haven't show here is the subsurface one. I mean the rupture. So there are some projection issue. So we haven't put the rupture propagation in the subsurface. So the subsurface is empty. But we will do that so people can just, it will be very valuable to show people how the energy emitted from the source of the earthquakes and how they propagate in the subsurface and finally interact with the cities. So thank you. Yeah. I'll leave my